So this is chapter 9, problem 1, which says find the change in the force of gravity between two planets when the distance between them is decreased by a factor of 5. So the gravitational force between these two planets would be F equals G times m1 m2 divide by the distance between them squared. Okay, so now I'm going to take one of the planets here and I move it 5 times further out. So there it is. And now the force is going to be G times m1 m2 divide by 5 times the original distance squared. Of course, this is 25, which is in the denominator, so on the other side means that I divide that by 25 or multiply with 1/25. So the force is 1/25 of the original one when it's moved out 5 times the original distance. Chapter 9, problem 2, which says the value of G at the Earth's surface is about 9.8 newtons per kilogram. That can be also written as 9.8 meters per second squared. What is the value of G at a distance from the Earth's center that is 4 times the Earth's radius? So here we would have G equals 9.8 newtons per kilogram, or meters per second squared. Those two units are synonymous. And now we're moving out 4 times further. So there we go. And then of course the question is, well, what's the gravitation out there, the acceleration due to gravity? Well, what we have is we have the gravitational force G times m times the mass of the Earth. That's a symbol for Earth. Divide by the radius of the Earth squared when we are at the surface of the Earth, and that equals this is Newton's second law. So the force on the left hand side and on the right hand side we have the mass of the object being accelerated with an acceleration a, which we call g at the surface of the Earth. Notice that the mass divides out, so it doesn't matter what object it is, they all are accelerated with the same g at the Earth's surface. Okay, so now we go further out and we're going to say, okay, we have g times the mass of the Earth divide by, now we're 4 times further out, so 4 times the radius of the Earth, and that needs to be squared. And now we get a fraction of g. Well, how much? 1/4 squared, which is a 16 denominator, or 1/16 of g, and therefore g out here is going to be 9.8 divided by 16, which is 0.6 meters per second squared. So relatively small, but definitely there. Chapter 9, problem 3, which says show by algebraic reasoning that your gravitational acceleration toward an object of mass m at distance d away is a equals gm over d squared, and therefore doesn't depend on your mass. And actually, I kind of did that in the last one. So here we have, I guess, a planet, and then here we have some person near it that is being attracted towards that planet, and of course vice versa. That makes The force is the same on either one, but it makes more of a difference to the small mass. In any case, we have a gravitational force of one object, object M, towards object capital M, and the two are a distance d squared away. And since there is a force between them, there's also going to be an acceleration between them. And of course, Newton's second law says m times a. And now what happens is that this m here would be the person, and therefore the mass of that person would divide out. If we had looked at the planet, then we would have written a capital M on the other side, and the mass of the planet would divide out, and then we have a much smaller mass left here, and therefore the acceleration of that planet would be much smaller, which makes sense. Both of them experience the same force towards each other, but because of the person's much smaller mass, the acceleration is much larger towards the planet than vice versa. The acceleration of the planet is much larger. I'm sorry, the other way around. The acceleration of the person is much larger towards the planet than vice versa. The acceleration of the Earth or the planet is much smaller towards the person. Notice that this is from one object to the other. I'm not sure if I said it correctly or incorrectly the first time around.